谢谢，请，那我就感谢你。Right， 朋友 ，you ready?
Would like to thank all of you for your continued support to the journal. Tsinghua University works on energy storage, and we also have Dr. Sammy Low, who is the managing editor based. And we would like to thank your next manuscripts to the journal. And
thank you, Jane. Thank you very much. So good morning, good evening, and everyone. Thank you very much for joining this webinar series. We had a very fantastic webinar series last year, and this is the first one for this round. So we are going to have webinars in this similar formats every month, roughly about 1 week or slightly morning or Beijing time, or Wednesday, or I think it's a Tuesday evening in the US time. Sometimes we also do that in the late afternoon of the Hong Kong time, so that the European audience can also join our session easily. Okay, so today, can we switch to the next speaker's topic? Right. So today we are very glad to have two world-leading academics on this topic for solar thermal energy conversion harvesting usage. Now, let me introduce the first speaker first. And our first speaker, Professor Peng Wang, who is also a colleague of mine in Hong Kong PolyU. So he's now an associate professor in the Department of Environmental Engineering, which is one of the top areas in PolyU actually in the world. So he has been working for quite a long time actually, a couple of years ago in KAUST in Saudi Arabia, also in a similar topic. And recently he moved to Hong Kong and become my colleague. He is quite well known in the world for his material and the device engineering. engineering towards this solar thermal energy. So I think I'm not going to give take too much of his time. And so without further ado, I would like to invite Professor Wang at Solar Energy Water. And please, during the talk, and we have colleagues to collect your questions after Professor.
Okay, to be part of this very important webinar series. I'll share with you some of the progresses in my group on this very general topic on energy-water nexus. To start, I do not think I have to convince you that water is essential for everyone. However, as you can see from this figure, it is now very widely predicted that in about 20 years' time from now, by 2030, more than 80% of the global population will have a high chance of experiencing freshwater scarcity or constant freshwater scarcity. And we blame global warming, climate change majorly for this. You take a look at the map. You have the almost entire United States, mainland China, being in very red state. That means that we will have very high chance of having constant freshwater scarcity in 20 years from now. Now, on the other hand, solar energy is abundantly available for most of us, if not all of us, to use. If you do your calculation correctly, your calculation will tell you that the amount of solar energy that the Earth receives within just 1 single hour is already more than what is needed to power the entire world for 1 full year. Solar energy is clean. Solar energy is free. So we should use solar energy as much as possible. Personally, I further believe that solar energy should be in the center of our fight, our effort against ongoing and ever worsening global warming. Now, what do I mean by sustainability at solar energy water nexus? Well, for me, it's my personal opinion. It involves two aspects. On the one hand, we should use solar energy as much as possible to help us to produce more fresh water, especially to produce fresh water at decentralized scale from unconventional water resources. Now, the second aspect of the sustainability at the solar energy water nexus is that we should utilize water resources, especially unconventional alternative water resources, to help solar energy to give us more electricity. With those two aspects within the same picture, we can have an ultimate sustainability at solar energy water nexus. I hope those couple of slides give you an engaging background of what I will be talking to you today. So today, in the next 25 minutes or so, I will be talking to you on our research progresses in the next two topics. The first one is solid distillation. So in this part, I'll talk about the recent progresses in solar water evaporation, as well as in freshwater production. Now, in the second part, atmospheric water harvesting, I will be talking about some of our progresses in sorption, fully solar energy driven, sorption-based atmospheric water vapor harvesting, as well as its application to PV panel cooling. And as you can tell, since I will be covering so many ground, my introduction to this topic can be kind of brief. So if you have any question, feel free to ask me after my my talk. All right, so let's start with the first one, solar distillation. Now, you may or may not know that the first solar distillation device was invented 500 years ago in the Middle East by Arab alchemists. Now, the general design principle of solar steel has not been changed significantly ever since it was first invented 500 years ago. Now, if you take a look at the figure at the bottom on the right-hand side, on the left-hand side, for a conventional solar steel, it works this way. You have the solar light coming into the system, heat up the bulk of water. Then you have water evaporation. Now, vapor condensation on the internal surface of the transparent cover give us fresh water. Now, from the modern science point of view, now we see that such a conventional or Asian design has two clear drawbacks. Now, the first one is that this system has low water evaporation rate. The second drawback is that it has relatively low vapor condensation rate. Now, with those two drawbacks together, a typical conventional solar steel, as I show in this photo on the right-hand side, is not able to give us fresh water production rate more than 0.5 liter out of 1 square meter of the solar absorption area each hour. So I will be using LMH for short as the water production unit throughout of the presentation of my part. Now, many efforts have been made to enhance the water evaporation rates, to enhance the vapor condensation rates, especially in the past 5-6 years in the general area of solar distillation. So in the solar evaporation efficiency enhancement part, I here have a brief summary of the major progresses in the past 6 years. As you can see, there have been a lot of photothermal structure design that help to enhance the solar evaporation efficiency in the past 5-6 years. As we know, if you shine light, solar light, directly on the bulk of water, you wouldn't have bulk of water heating scheme. In that case, the solar evaporation energy efficiency is no more than 25%. So in 2014, 2015, there was this very popular concept or scheme of interfacial heating. Right? So this scheme is as simple as floating a photothermal structure directly on bulk water surface. Now, with this simple design, you see you can boost the energy efficiency all the way to 56%, which is very significant advancement compared to the bulk water heating that give you 25%. Now, about 1 year later, people realize that you have to stop the photothermal heat from going into the bulk water. At that time, there was a design of having the not photothermal, but the thermal insulator layer to have a dual function of thermal insulation and water delivery channel. Now, with this design, the efficiency can be further enhanced to 73%. But later, people realized this was not ideal, all right? So the much better one was to have those two functions, thermal insulation and water delivery functions to be separated, physically separated. That's why in 2017, we had this two-dimensional water delivery design. I can tell you that Professor Zhu Jia, who is the next speaker, contributed significantly to this design. In 2018, there were some three-dimensional photothermal designs combined with one-dimensional water delivery. The system can give us an ideal, almost perfect solar evaporation efficiency. Close to 100% energy efficiency can be achieved. You know what? Now, for some of the design, due to its enlarged water evaporation surface, it can even purposely created some evaporation area that has temperature lower than the ambient air. Therefore, for such a design, it's possible that it can harvest energy from the environment. You call that ambient heat or environmental heat. Now, with this design, you would see some system is able to produce solar evaporation efficiency more than 100%. I call that apparent energy efficiency. All right. So moving on to the second part of the vapor condensation design. Now, for this part, I have to mention one work from Professor Asinari in Italy. In 2018, he published this design of multi-stage membrane distillation with the photothermal conversion. You see in this design, the photothermal material is on the top that absorb the solar energy and convert the solar energy to heat. Once you have the heat being produced there, now the heat will flow into the multi-stage membrane distillation one by one. Now, when the heat is going through one stage, the vapor condensation latent heat of this stage will be recycled and reused as the energy to drive the vapor evaporation or water evaporation of the next cycle. Now, as you can see with this design, the system can utilize the same amount of the incoming solar energy for multiple times. Therefore, it's expected that it can lead to higher freshwater production rate. All right. So, however, this system has a small problem. You see, seawater comes in, freshwater comes out. there's no other channel for the salt to go out. Therefore, the salt will be accumulated inside the system. We call this dead end. Dead-end flow design is not practical for practical application, so it cannot be used for continual application. Now, I just want to very quickly switch to PV. Now, as we know that PV is nowadays the most popular, the most important renewable energy for us. However, PV is not without any problem. As a matter of fact, it has a very serious problem. The commercial PV has solar to electricity efficiency between 10 to 20%. Now, this is to say that for the commercial PV, it has more than 80% of the absorbed solar energy not being converted to electricity, but converted to heat as a waste. Therefore, PV has a very serious problem of overheating. Now, in one of our projects, we find the waste heat of the PV panel a purpose. Now, this is our design. We call our design as photovoltaic membrane distillation, or PVMD for short. Now, as you can see, in this design, we use the waste heat of the PV as the energy source to power our multi-stage membrane distillation to do seawater desalination to produce fresh water. Now, the heat, once produced by PV, flows into the MD part naturally, driven by temperature gradient. And another small contribution we made to this is that, as you can see here, for this design, we have a cross flow. We have a cross flow for our PVMD. Cross flow in this design make the system able to operate in a continuous manner. You see, you have seawater comes in, you have fresh water comes out, and the produced concentrated brine also flows out from a different channel. So this way, we can use this system to do continuous seawater desalination while with the PV to produce its regular electricity. So we fabricated, based on the design, our first generation device. Now the results of our first generation device is presented on the top part of this slide. And you can see for that device, we were able to produce the freshwater production rate 1.8 to 2.0 LMH, which is already a much higher number than what regular conventional solar steel can give us. Now, I'm very happy to tell you that this paper, since its publication in 2019, in the past 20 months also have been read, accessed for more than 50,000 times. Now, that was what we did in 2019. Ever since, we have been continuing working on this. Now, in one of our latest devices, the device is able to produce fresh water production rate close to 4.0 LMH. And what is more is that at this point, we can make the water distillation part or MD part to be able to help the PV panel to reduce its temperature by a certain extent. Now, with PV panel temperature being reduced, you can expect that the amount of electricity the same PV can produce will be increased. So this is something we are still working on, and I hope I can have some exciting progress to share with you soon on this. Now, to summarize this part, I want to say that PVMD has many benefits. It can utilize solar energy to its full capacity. It can effectively produce both electricity and clean water from the same device, same PV device. It can help PV to enhance its electricity production due to the cooled PV panel. And we are currently working on making such a system not to produce brine. Instead, the whole system can produce fresh water and pure mixture of the salt. We call that, once there, zero liquid discharge. We are not there yet, but we are working toward that direction. Now, moving on to next topic, atmospheric water harvesting. As you may or may not know, there's really a lot of water in the atmosphere. The amount of water in the atmosphere, including solid, liquid, and vapor, is more than 6 times all of the water in all rivers on Earth. And the water in air is typically clean and fresh. Therefore, we just need to figure out energy efficient way of taking this precious fresh water home. Now, in the past 7 years, 6-7 years, we have been working on fully solar energy driven, sorption based atmospheric water vapor harvesting processes. For this system, as you can see from this slide, it works this way. You have to have a special vapor sorbent to start. Now, this sorbent can absorb, can harvest water vapor from air, typically at evening time or nighttime when the temperature is low and the relative humidity is high. So the water, once inside the sorbent material, will be stored there as majorly as liquid water. Now, next day, when the sun is up, you're gonna take the material out and let sunlight to heat up the material. With a high temperature, this material will release water as vapor. So long as you do the whole process within an enclosed system, vapor will be condensed, and this is how you can get your fresh water this way. Now, we started working on this process in 2015-2016, and when we started at that time, we started with a special salt that can absorb vapor from air by hydration reaction. So, as you can see, at that time, we worked with copper chloride, copper sulfate, magnesium sulfate. Those materials are okay because they work with the relative humidity being very low, and because they only produce small amount of the fresh water. In the example of chloride, copper chloride, we got the water production rate of 0.21 gram of water, fresh water out of 1 gram of this sorbent material per day. Now, of course, we're not happy with this small number of the water production capacity. Therefore, we later move on to work with deliquescent salt. In that case, we combine deliquescent salt, in this case, calcium chloride with PM hydrogel. The material is shown on the right-hand side. Now, with this design, the water production rate can be significantly increased to 1.75 with the relative humidity being 80% and 1.1 with the relative humidity being 60%. However, this material has a problem of slow kinetics for water vapor absorption and also for vapor desorption. Now, in the third design, we call that third generation, we turn to nano design to improve or enhance the vapor absorption and vapor desorption kinetics. Our design was this. So we designed some nano container and we drop the deliquescent salt into the nano container with the purpose of increasing the contact surface area between water vapor and deliquescent salt. It really worked. It really worked. And you can see with this design, when you have the material being illuminated by simulating the solar energy, solar light, you have very immediately release of the vapor. So with this design, we were able to do 3 sorption-desorption cycle within 1 day, which is a very favorable result because for the previous design, we were able to do only 1 cycle per day. Now for the next design, since we got 3 cycles for the nano design, we asked ourselves, can we go all the way? Can we have a continuous design? So the small machine here is our prototype, very primitive. It provided the proof of concept that we can design such a continuous process to continuously produce fresh water from air vapor. However, the performance of our proof of concept or prototype device is not very good. So we are still working on improving the efficiency this week. Very recently, in about, I think it was last month, we produced a metal halide-free solid-state polymeric water vapor solvent. The reason for making such a material is that we know that when you have chloride in your solvent, which is actually the case for many salts, many polymers, chloride is corrosive to metal plates that are typically used for AWG, AWH devices. So we had this design of having this chloride-free solid-state polymeric water vapor solvent to specifically target that problem, corrosion. And for this generation of the material, the corrosion was minimized. However, the water production performance is still not so fantastic. We have to work hard to make this material to be able to produce much more drinking water or fresh water from air vapor. So we are currently working on this. Now, very quickly to move on to the cooling part. Now, as human, we sweat. This is how we actually modulate, stabilize our body temperature. We know that PV has an overheating problem. So at one point, our student was thinking, can we actually tap into atmospheric water vapor to help PV to cool? Here is his design. You see, the design is actually pretty simple. So in this design, so long as you have your water vapor solvent material stuck on the backside of the PV panel, in the evening or at night, those materials on the back will secretly absorb harvest vapor from air. Now the vapor, once inside the material, is stored inside the material as liquid water. right? Next day, when the sun is up, you see the PV is heated up. The heat flows into the sorbent layer on the backside. Now, the sorbent is heated up. Now, this will drive water to evaporate out of the sorbent. Now, water evaporation takes a lot of heat of this system. Therefore, it is our hope that such a design can reduce the temperature of the PV during daytime. Therefore, with the reduced temperature of the PV, we should expect that the same PV will give us more electricity, right? So this is our design principle. Now, to prove this concept, we simply went back to our second generation material. If you still remember, it is calcium chloride with PM or composite hydrogel. Now, we took the composite hydrogel, put it on the backside of a commercial PV cell. You see, I'm pointing to the hydrogel layer on the backside of the PV cell. Now, as you can see from figure C on the right-hand side, without the PV, without this hydrogel on the backside, the PV or PV cell had about 65 degrees Celsius under solar irradiation. Now, the same PV with the hydrogel had the temperature around 35, 37. So temperature was reduced significantly. And in our indoor laboratory tests, outdoor field tests, the best outcome or the best results we got was that with this simple design, with this simple atmospheric water reabsorption desorption cycle induced PV cooling design, in some cases, the same PV panel could produce more 19% more electricity than the same PV panel without this atmospheric water harvesting induced cooling design. Now the bottom right are two photos which show the gradually scaled up the device. As you can see here, for this design in the middle, you see we actually have a metal chamber on the backside. The design of the metal chamber in this case is to, in some cases, if needed, the whole system can actually help you to get some fresh water. Now, I believe a small amount of fresh water is very important for PV. Why? Well, if you have been in dry area where you have a large PV farm, dusting issue is very serious for PV there. Therefore, with small amount of fresh water locally produced by each PV panel, you can think of using that precious water to help clean the dust off the PV surface. All right, so that's pretty much I have for you. Now, I just want to very quickly to summarize my presentation and say that there are a lot of challenges at the water energy nexus, and therefore there are a lot of opportunities at the water energy nexus. Now, the real solution, effective solution at water energy nexus calls for solid collaboration among scientists in different fields. So let us work together to push our world towards the ultimate water and energy sustainability. With that, I give the floor back to Zijian.
Okay, Peng, thank you very much for fantastic talk. I can see there's quite some remarkable progress actually in your group in the last couple of years. And happy to see that you also keep on pace of getting better jobs done when you move to PolyU. So I have collected, Bo has collected quite a couple of questions. And so I would like to ask here. So I think after asking, maybe there are more questions coming in. If there are, I probably will ask you again after Zhu Jia's talk. Is that okay to you? Right. So some of them are written in Chinese, so let me translate. And I'll probably combine the similar topics together. So I think one of the topic asked is about this distillation. And particularly in seawater harvesting. And I think that's related to the recent topic about this pollution or radioactive materials that being disposed into seawater. So in your technology or in this distillation technology in general, would there be any leftover of these irradiative materials after you get the water? And if yes, how do you get rid of them? Or is there any better technology or material in principle that can tackle with this problem? Thank you.
That's very fantastic question. It's very timely, very well relevant. So, I have to be honest with you. We haven't looked at this problem, but I do not think this will be a big issue for two reasons. First one is that the radioactive material, contaminants in water, they tend to first not volatile. Therefore, for all kinds of thermal-based desalination process, they will not be evaporated along with water. Therefore, they will be left behind in the concentrated brine produced by the system. And secondly, if you are really concerned about small concentration of radioactive chemicals in the raw seawater, I believe there are effective solvent material existing in the market, and you can have this as a pre-treatment part to selectively remove this small concentration radioactive material out of your raw seawater before letting the water to get into your membrane distillation system. So I don't have large concern with this.
Okay, so I think a related question to this is also, how about for those salts? I mean, in general, there must be some salts in the air or dust, right? So how you get rid of those, or is there a problem? Because you're gonna need to stain your device, for example, your PV panel or your parts. Exactly. It's gonna be corrosive.
So, yes. So first, I assume that this question was on the atmospheric water harvesting process, right? Of course, this is an obvious issue. Now, there are potential solutions to this. Now, those things you mentioned belong to macroscopic, scale, and the material, the atmospheric water vapor solvent, works with vapor molecule. So there's a mismatch between the scales. Now this mismatch can give us solution, but we do not have to have the solvent material to be fully open to the open air so that the material can harvest vapor from air. It is that you can have closed system, not fully closed, but you can have some special design, like a screen type of shield that can keep those macroscopic substances from making physical contact with your solvent. Now the solvent is always able to harvest molecules, water molecule from air. So this, as long as you have, this shield design, should not be a big problem for atmospheric water harvesting.
Right. So I think what you meant was so to probably physically block this slightly bigger scale or much bigger scale particles from the atmosphere, so that you can still allow the moisture or water molecule to go through this membrane and then get collected by the absorber, right?
Yes.
Yeah.
Exactly.
So, okay. So I think this is quite two key questions. Other questions, some of them are related to your hydrogel, actually. I think it's the last parts or last two parts. Now, I think this is very specific question. For the PAM, CNT, calcium chloride hydrogel material that you mentioned, what are the advantages of CNT compared to other carbon-based material? Since CNT is probably slightly more costly than carbon black, of course, or biomass-derived carbon. So I think that's what they're asking. What's the advantage of CNT, or if you can replace by other better, or cheaper carbon?
Yeah, very, very good question. So, the use of the choice of CNT was in our project convenience based, and this is to say that I personally don't believe that CNT is better, at least in our material, than what you mentioned as like a biomass derived carbon, right? So we now in this project we have compared different photothermal materials. We compare carbon black, carbon graphite oxide, carbon nanotube, and all of those materials give us very similar, solar thermal conversion efficiency. So for that, I would say, so long as you have the much cheaper material, like carbon black, that can give you similar photothermal conversion efficiency. If it is for practical application, you should always go with this inexpensive material. Right.
So follow up with that, for this hydrogel or material, one question also raised is that so you design a very strong water absorbing material, and I think the last part you said you're going to install there and using this evaporation or water vapor under heat to cool your PV. So, but I think in your second part you also mentioned that you are going to collect the water from the moisture. So once you get a very strong water absorbing material, how do you get them out? Because that it also takes energy, right? So how do you going to balance this, or how you design a better system?
Exactly. This is another very important question, and I appreciate this question because this gives me a chance to actually clarify some things in this atmospheric water harvesting research field. Now, you are exactly right. You cannot, for the atmospheric water harvesting, for the purpose of producing drinking water, you cannot use the solvent that has very strong absorption heat. Now, you cannot typically use zeolite because zeolite can give you very, very strong or, very, very large absorption heat for water. You can have the absorption part very fantastically. However, once you have the material inside your, not the material, the other way around, the water inside your material, this is zeolite, you will have very difficult time of getting the water out. So for the atmospheric water harvesting material, there has to be a wisely chosen reabsorption heat of the water vapor into the solvent. we do not favor those solvents, especially zeolite, that sorbs water vapor very strongly. All right, we choose something, something with much lower absorption heat. So I think, okay, because the audience cannot respond. I assume that I addressed your question.
Right. I guess what you meant is that what are the good materials, but the best water absorbing material may not be the one that you actually want for this kind of application, right? You look for balance. I think that's probably what you meant.
I want to say. Okay. Yeah. Yes.
Okay. Great. Thank you, Peng. I think our time for your session is just up, right? So I would like to switch your microphone to Zhu Jia.
Okay, let me.
Hi, it's Jen.
Okay.
I'm here.
Yeah, Peng, you want to say something?
No, I would like to welcome Zhu Jia.
Okay.
Thank you.
Thank you, Peng. Let me thank you again for a great talk. So, Jia, you are you okay with all your microphone and setting, etc.?
Yes. Can you hear me?
Yeah. I think I can see your face now. Great. So let me very briefly introduce you. So this is Professor Zhu Jia, and again, a very young and a world-leading scientist in this field. I think compared to Peng, probably you are studying more on the materials aspect point of view, right? For the development. And so Jia is now a professor at the College of Engineering Applied Science in Nanjing University. So I think his interest has been in this nanomaterial, nanophotonics, nanoscale heat transfer. So again, introduce very briefly his background. So he was a bachelor in Nanjing University, and then get his PhD from Stanford under, I think, Choi Yi, am I right? And
yes.
then work as postdoc in UC Berkeley and Lawrence Berkeley National Lab. Then come back to Nanjing a couple of years ago, quite a few years ago, I would say, and then work until now. He has already received a large number of awards, one of which I think I want to mention recently by the Chinese government is this NSFC Young Investigator Award, which is very prestigious, and several international awards, Explorer Prize, that's by the Tencent funding, am I right? And then this Tangen Yi Young Scientist Award and others like DuPont Young Professors Award. These are all very prestigious awards. And then when he was still a little bit young, I think that was you got this MIT 35 under 35, right? When you were still eligible, right? Okay, so I think today Zhu Jia want to talk about this, how to manipulate the flow and light of heat at the nanoscale of materials. And Jia, I will hand over the microphone to you.
Well, thank you, Zhijian. First of all, I'd like to thank Zhijian for the leadership, and I want to thank the colleagues at Wiley for providing this great platform. And also, I want to congratulate Professor Peng Wang for all the great results, and nothing could serve a better introduction for what I'm going to talk about. Some of the things I think will be on the similar theme, but of course I will talk about several other efforts in the group. So can everybody see my presentation?
Yep.
Great. Let's see if I can minimize this. All right. So the title of my talk today is about manipulate the flow of light and heat nanoscale. So there are two abundant energy forms in nature, light and heat. Actually, as a result of that, photothermal effect playing critical roles at several scales. Let's see. Yes. The first photothermal effect I want to talk about is at global scale. It's what we call water cycles, right? As a result of photothermal effect, the water evaporates and transport and precipitate. There, as a result, the water is purified through these processes. It is a great process supporting the water for the civilizations. But we're going to talk about how do we improve the efficiencies and through material designs. And second photothermal effect is at the microscopic scale, and it's really talking about plasmonics. As people know, plasmonics is a collective oscillation of the electrons responding to the photons, right? And because of these oscillations, there is ohmic loss, and heat is generated as a result of that. So we're going to demonstrate that. How do we develop new materials and structures to minimize these plasmonic losses towards the integrated photonics devices? And the third photothermal effect is at the galactic scales. We know that the temperature of Earth is balanced by the Sun and colder universe. The Sun is around 6,000 K and colder universe is around 3K. So, and because the environment, the Earth is balanced at 300 K. So, and all the energy transfer is largely done through radiations. So, we're going to demonstrate how do we take advantage of this photothermal effect to provide a passive cooling through radial cooling. So let me start with the first one, water cycles. I think Professor Peng Wang has provided a very nice and detailed introduction about why do we want to do the solar evaporations. Water is really a big issue, and the natural evaporation is a great process, but it's not very efficient. For very obvious reasons. Water is not a good absorber, and all the water, the light get absorbed by water is only induce the bulk water heating, right? So that's the reason in the past few years people are trying to do interfacial solar evaporations, namely just put absorbers on top of the water surface to flow naturally, and light come in and evaporate the waters, right? And in order to enable efficient solar evaporations, and we want to do photon management to improve the light absorption and to do the heat transfer to minimize the heat losses, and also want to do the materials, the structural designs to provide a continuous water and vapor supply. So in the past few years, we have tried to develop various materials structures to improve the efficiencies and also at the same time lifetime. I think people ask about the water, the salt clogging issues and a few other issues, and there is all related to the lifetime as well. So now where we stand is that without any external optical concentration or thermal insulations, our efficiencies can stand over 85% under the natural conditions, and the device can work quite well even when treating the high concentration wastewater. So one of the common questions people ask, well, can we understand like interfacial solar evaporation as an absorber just floating on the water? Can we call that interfacial solar evaporations? Well, largely, I think that definition is kind of blurred. But in my opinion, if it is a true interfacial solar evaporations, meaning the absorbed sunlight will generate heat, and the heat will only heat up the top layers of water molecules. That means that what we call interfacial solar evaporation, right? So if that's the case, then how high the containers, or how high the water, how thick the water layers won't matters, right? So the efficiency shouldn't be depending on the water quantities. I think that will be a signature of true interfacial solar evaporations. And that kind of experiment is demonstrated in our PNS 2016 papers, right? So if people want to examine whether it is interfacial solar evaporations, I think that's the experiment you can try. You can try different containers and try to see whether efficiency will drops as the water quantity increases. Of course, the way we do it is we're providing this two-dimensional water path to minimize the heat conduction losses, so that the heat localization can be achieved. The efficiencies there, as a result, can achieve the interfacial solar evaporations. Of course, there will be various other ways to achieve that, but I want to emphasize that not any absorbers floating on the water surface will be called interfacial solar evaporations. I think that's something we need to be aware. And one of the targets is that to provide these personalized water solutions, essentially with sunlight, with just water sources, right? You can produce a clean water by yourself through these portable devices, and that's something we're trying to do. And very quickly, I want to report some of the recent progresses, maybe not so recent now. And the first one is that because more and more people are jumping, this is now a very active field of solar vapor generations. So I think we received quite a lot of inquiries on how to do the measurement correctly. As any energy devices, right? You want to do the measurement correctly. So we, together with a few other groups, were reporting we're trying to build the first protocols and standards to measure the solar evaporation efficiency correctly. Actually, as efficiency and evaporation is very sensitive to various parameters like temperature, humidities, and windy conditions. So there are a lot of details you need to check. And also, you cannot keep all the conditions consistent, right? I think the condition in Hong Kong is different from the one in Nanjing, and it's also different from the one in California. So we also list all the parameters that might affect the evaporation performances. And you don't need to be consistent, just need to report all the conditions honestly so that people can do the cross-check and you upload the things you want to do. I think that's hopefully can set up a protocol for people to jump in and to build a sustainable communities. And also, people working on solar energies, they might think there's an upper limit for the evaporation efficiency, evaporation rate, right? Assuming there is a standard solar spectrum on AM 1.5G. So, and you assume that the enthalpy of the evaporation, then you can calculate the evaporation rate is around 1.47 kilogram per meter squared per hour. I think in the past few years, people start to realize, well, not just the sunlight can evaporate waters, you can also harvest the energy from the environment, as long as the temperature of the environment and can be lower. Temperature of the absorber can be lower than the environment, then you can harvest the energy from the environment to enhance the evaporations. And so 1.47 kilograms per meter squared per hour is not considered as an upper limit. And the recent results, we reported evaporation rate over 10 kilograms per meter squared per hour, taking advantage of this convective flow so that you can further enhance that. I think that's actually good news, so that you can treat the water through evaporation at a fairly high rate and without consuming the active energies. Another, I think, areas worth exploring, and Professor Peng Wang also did fantastic works in this field, is that how to harvest the water from the air. If you want to treat the water, you need to have water source in the beginning, right? If you don't have water sources, and one way to do that is to harvest from air. I see that there is a question from the audience saying, what interfacial solar evaporation can do for the when you harvest water from air, because there are always trade-off between absorption and desorption, just like catalytic processes, right? For the good absorbers, it's hard to dissolve it, right? So it's always a trade-off. I think the key for interfacial solar evaporation is that you can concentrate all the energies interfacially, meaning at the top surfaces, so that you can enhance the desorption, so that you don't need to worry about desorption. You can use very strong absorbers to do that. I think that's a key for the interfacial solar evaporation to play a key role in this field. And as an example of demonstration, we use just calcium chloride solutions, and it's a strong absorbers, and we put graphene oxide materials, and they have a large pore sizes and structural designs so that you don't have a salt cloaking problems. And you develop that, you enhance the desorptions and put that on a strong absorbers. And at under the condition of Nanjing, you can get close to 2.9 kilogram per meter squares, and through a few hours. I think that's something we can do, and that's a role interfacial solar evaporation can play to improve the water collections from the atmosphere. And another things we are very interested in is zero liquid discharge. That's I think quite a few people in the water treatment field has been very curious to know about. I think for the wastewater treatment, the ultimate goal is that you don't create any liquid discharge. So that's what we call zero liquid discharge. But it has been very difficult because, for example, if you use membrane devices, right, you produced water, purified water. At the same time, you also concentrated the salt waters. So once it is over certain concentrations, then it's very hard to treat it with technologies like RO. And so high concentration brine is a difficult one. So, and we also try to see whether, well, for the traditional membrane technology, it's hard to treat, then can we do that through evaporation approaches? Of course, it's not trivial. I think the previous a few questions have been asked. Once water is gone, right, where does salt go? And naturally, salt can get stuck on the absorber surfaces, and then they block all the water vapor pores and water supplies. Then they will cause lifetime problems. But of course, that problem is not a natural thing. For example, when you see the seawater evaporating, it happens all the time, but there's no salt coming on, right? Because there is a water flow coming, keep diluting all these concentrations, right? So in the past few years, we have been putting quite a few effort, including all the efforts from other groups. But there is always a trade-off between efficiency and lifetimes, and we want to break that trade-off to achieve the efficiency and lifetime at the same time. One of the examples, recent examples, is we call it water lily structures. And a few key features is that water lily structures, they have the super hydrophobic surfaces, so that the water cannot get into the absorbers, right? So it's at, I cannot, whether people can see that, but the water only touches the bottom surface of the absorbers. And at this interface, evaporation happens. The water goes, and the salt, they build a concentration gradient, which helps them diffuse back. So that's one of the key features. Of course, you have light trapping effect to minimize the optical losses, and you have this heat localization design to minimize the heat losses. Therefore, to maintain the high efficiencies. And the devices can be fabricated through different approaches. And in our cases, it's through the copper foam and nanostructure with the surface treatment. And it can be fabricated through large scales. And as you can see, no matter how you treat the waters and what kind of water it is treating, like DI waters or wastewaters, efficiency can be always maintained over 80%. And all the water collected out, the quality has been very good. And as you can see, this water lily structure design will treat the high concentration brine. As the water evaporates, there is no salt accumulated on the surface. But for the conventional structures, as water evaporates, there are always salt stuck on the surfaces, which will degrade its performances. And when you treat the high concentration brine, we're talking about over 10% brine waters. As you can see, this is an outdoor test, right? As water evaporates, just the surface comes down, and you see there is no salt coming out at all. At the end of the day, when all the salts, when all the water goes, and there is no salts on the surfaces, and when you opens up these materials, you see all the salts deposited on the container. That means it achieved the complete separation of water and solute, and that's what they call zero liquid discharges. It's also happening when you treat the 30% wastewater. So I think that's actually good news. That means for the evaporation approaches, you can achieve that zero liquid discharges just pure through the solar powers, and that opens a lot more opportunities when you treat the wastewaters. And the four stories I want to share is when you consider solar evaporation as a solar energy conversion devices, you naturally will link that to the PV devices, right? The PV devices, we know that they have a shock liquidity limit close to 30% efficiency, depending on how you calculate that. So the real energy has been used is in this part, right? And so one of the natural thinking is that, well, you can use a full spectrum utilization for the above band gap photons. You can harvest that through the semiconductors. And for the below band gap materials, the photons, you can use that for solar applications. But one of the further thinking is that perhaps you can even take advantage of this purple part, because this purple part, they will do harms to the PV, they will heat up the PV. But if you can transfer that part of energy to the bottom cell, you can utilize that for evaporations, and also you can cool down the devices. Actually, it's I think the Professor Peng Wang reported similar results independently, and we're thinking about from different aspects, but we come to these problems naturally from different aspects. But the key is to develop these interfacial thermal films to help the heat transfer from the top cell to the bottom cell. At the same time, you don't want the vapor goes into PV, so you want to minimize the penetration rate, right? So that you can protect the PV from the vapors. So that's the result. That's the reason we combine EVA with CNT, because CNT provide a high thermal conductivity, while EVA is a natural packaging materials for PV devices. As a result, we can generate electricities. We improve the PV efficiency from 19% to 20.4%. And all at the same time, we're harvest over 50% solar energies for water productions. So you can produce water and electricities at the same time through affordable solutions. Everything can be put in your bag. I think that's something I think is neat. So I think for the individual solar applications, we think there are still huge opportunities right there from both the fundamental perspective and application perspective. The water behavior at the nanoscales, actually, we know quite little about it. I think we don't even have enough tools to explore that. I think there are a lot of things need to be done and can be done. And also, from the application perspective, the vapors or steams actually very useful forms of energies. You can use that for food, for electricity, for sterilizations, for waters. And with sunlight and water resources, you can produce those basic needs, right? I think that's very powerful technologies, really enable many other things as well. So we're going to following this path, and we're going to stick to that. Hopefully, we can report more progresses and for the next opportunities. And the second photothermal effect I want to talk about is that this plasmonic ohmic loss. There's oscillations of electrons responding to the photons. So as a result, there is ohmic loss coming out of that. So in the past, I think decades, people are trying to develop these low loss plasmonic materials. I think people familiar with plasmonics would know that traditionally people have been using these noble metals like silver and gold because of the low loss. But their loss has been not ideal for many applications. People have been searching for other low loss plasmonic materials. And as you can see from this 2011 perspective by Professor Henrietta Walter and Bodhisattva from Purdue, acrylic metals has been considered as an ideal plasma materials, but there have been no experimental proof that it can be a low loss materials. I think in the past few years, we actually have been working on that for I think over 6 years. And we kind of developed a very unique processes, taking advantage of the low melting point of the acrylic metals. For example, sodium, you can melt it once you heat up to 100 degrees C. And once you become a liquid, you can spin coat it on the quartz substrate. And it's actually quite convenient and processes. Once you spin coat it, then the surface roughness of these sodium films will be defined by the substrate. You can get a very high quality, high smooth quartz films. And as a result, you can get a very high quality, very smooth sodium films as well. And once we have that, we check the XRDs, high quality polycrystalline sodium films, and you measure the optical properties, and you find that our results, the loss is significantly lower than this noble metal in terms of optical losses. And those are particularly important at the 1.3 to 1.5 micron wavelengths, which is communication wavelengths. And in order to further prove this low loss of plasmonic materials is ideal for applications, we're collaborating with Professor Mari Ming at Peking Universities. His group has been dedicating to the Nano Laser development. So we're using our plasmonic sodium films and to build the Nano Laser devices. And it shows extraordinary lasing performances. And in terms of a threshold at similar wavelengths, right? It lays at room temperature, and the threshold is only around 140 kilowatt per centimeters, which is the lowest threshold. And the lowest threshold is achieved because of the low loss of sodium films. I think that's a direct proof of that. And as you can see, acrylic metal is outstanding plasmonic materials. And of course, we don't need to forget it is also excellent energy storage materials. People have been trying to do lithium metal batteries, sodium batteries as well. So we want to see whether the plasmonic signals can provide information for energy as well. So one of the things people, I think, working in the field of energy storage is that, especially for the lithium metal, is that they have the dendrite problems. Once you have this dendrite, it can penetrate a lot of things and it can cause all the safety issues, right? That's the reason so many explosions and shortcut burning issues for the batteries. So one of the things we think is that once different lithium metal have different plasmonic responses, right? If it's a normal growth, as in the case demonstrated above, then the optical responses, well, they have a very significant plasmonic signatures. But once you have these dendrite formations, because of the light trapping effect, can minimize this reflections quite well. So you can remove all the signatures of plasmonics. As a result, you can detect whether you have a dendrite formation or not. And you can perform these dynamic responses as the batteries keep working, charging, discharging. You can tell immediately once you have these dendrite formations, then all the optical responses will give you the signals saying that dendrite is coming. I think in terms of battery performances, dendrite is like cancer. You need to cure them. Of course, you also need early detections. And the optical way will provide real-time and early-stage detections for the dendrite formation. So we're very optimistic about this econometrical plasmonics. We think they're sitting at the intersect of the information and energy field. So there is a lot of things we can fully explore and along these directions. And the third photothermal effect is what we call radiative cooling effect. As we know, the Earth is balanced by the hottest in the universe, the Sun, and the coldest in the universe, 3K. So perhaps people are more familiar with the term global warming, right? Because these atmospheric layers, so they can block the radiation energies from the Earth, and as a result, it can cause a lot of issues. Actually, for these atmospheric layers, they leave a transparent window at 8 to 3 micron wavelengths. If the Earth is radiating energy through these windows, they will not be blocked. There will be. That means through these windows, the Earth can talk directly to the universe. So that's the beauty of the radiative cooling. Indeed, in the past few years, there is a lot of active efforts to develop these radiative cooling technologies. And one of the key features, ideal features, is that as only at a window of between 8 to 13 micron wavelengths are transparent. So you want your emission to be selective. That means they only emit at this window, but not in the other wavelengths. And I think through the calculation, you'll find that selective emitters will be more ideal compared to the non-selective ones in terms of cooling performances. So in the past few years, if you look at all the efforts, the real selective emitter devices is demonstrated in the initial daytime radiative cooling papers published in Nature in 2014 by Professor Xiang Huifan group. They are fabricated very, very beautiful and important breakthrough. Those selective emitters are fabricated through a 1D photonic crystal design. So it's multiple layers and through high vacuum processes. And all the other radiative cooling devices, they do not have the selective emission properties. So we start to think, well, can we develop scalable selective emitters to achieve a high-performing radiative cooling performances? And we turn to molecular designs, and we find that the emission in the infrared is actually directly linked to the bonding of the molecules. So if you choose the right bond, actually you can improve the emissions as well. And at the same time, you want to reflect the sunlight effectively. You can achieve that through the nanostructures because they are comparable to the visible wavelengths of sunlight. So you can do that through the nanopore structures and scatter the sunlight effectively. So as a result, we developed this nanofiber PO films, and we can achieve the high reflections for the sunlight spectrums over 96%. And you can achieve the selective emissions. We talk about 78% selective emissions. So, and we can produce these nanofiber films through electron spinning processes, row-to-row processes. And we examined that. We found that the cooling effect is actually very obvious. You can achieve over 5 degrees C cooling effect compared to the atmospheric temperatures, right? And you can achieve over 7 degrees C at the nighttime And of course, you can have lots of applications for that, because providing cooling without active energy consumption is actually very ideal, especially for the outdoor equipments, electronics, base stations, activities, and also buildings as well. I think that's provide a very quick sum up for what I'm talking about. I think we develop various technologies along to manipulate the flow of light and heat in nanoscales. And we just provide 3 examples in the field of solar applications and low loss plasmonics and the radiative cooling. I think this field is still very active and very excited about that. And we can, a lot of fundamental issues need to be addressed, and also we have a direct implications in various fields. And I think we will explore along these directions, and there will be more exciting results coming up. And hopefully, next time I can report more progress. And thank you very much for your attention. Thank you.
Thank you very much, Jia, for your fantastic talk about various materials for various application scenario. So I think the questions are popping up, right, as you may also see in the panel. Now, let me probably ask you, I think the questions are quite deep, though. The first question, specific from somebody, is that do you agree that the evaporation enthalpy of water can be reduced by the materials to achieve high photothermal efficiency as reported in some literature? Do you agree? So I think that's the point that is asking for your comment.
Okay.
About this design rule, right?
I see. Thank you. That's actually very good questions, and it's clearly from the people working in this field. And frankly, I have discussed that with Professor Wang Peng as well. I think so. Perhaps Peng, you can also chip in, right? I think that people has been reporting the enthalpy reductions, and they use that as explanation to explain the high evaporation rate. And I think that part it's a possible mechanisms, right? And they're providing some explanation for that. But so far, I think that it's not super clear to me exactly how the enthalpy can be reduced. That physical picture is not completed yet, at least to me. So I think I'm open to that. But I don't want the enthalpy reduction to be an excuse to explain all the extraordinary phenomena. I think that cannot be used as an excuse. I think also, as Professor Peng Wang also provided, that there are many other mechanisms that might cause the high evaporation rate. For example, you can harvest the energies from the environment as well, right? So we need to check whether it's the enthalpy reduction or it's other reasons. I think people need to be careful about that. Yeah, but I see there's a effort try to further explore along these directions, and we're open to that discussions. I don't know, Paul, do you have anything to chip in as well?
Yeah, I agree with Professor Zhu's comment. So we have really talked about this for quite a lot of time, and I fully agree with Professor Zhu's thinking that at this point, for us, we say we have not seen any system that can provide full proof of the reduced evaporation enthalpy. There are many competing mechanisms that can lead to high evaporation rate. So only when you can eliminate all other competing mechanisms in your system, you can fully prove this enhanced evaporation is from your reduced evaporation enthalpy. So I think if this mechanism is proven right, it's very exciting for the field because this can really help us to further enhance the water production rate, water evaporation rate for many, many exciting applications.
Okay, thank you. I think so. The conclusion seems like it's not that clear now, but obviously it might be one of the important aspects, but not the stage to explore other possibilities yet. And I think normally it's quite complicated in a real world scenario, right? It's always not from this very fundamental physics, physical chemistry issue. Right. So let me raise another question. I think this question relates to both of you. So again, is look for your comments about the perspective on the future development of interfacial solar stream generation. I think it's about this the first topic both of you have discussed about distillation or solar thermal conversion for water distillation, something like that. Would you mind? Who might start? Maybe Zhujia, you start with that. Any comment?
Sure. I think the general comment for that is that I think it's so interfacial solar evaporation will be very exciting and also diversified field. I think that it's people try to compare that with PV, saying it's an efficiency game, right? For example, you always want to boost the efficiencies. And I think it's beyond that. And the efficiency now has been improved, I think, thanks to all the efforts from all the worldwide groups, right? But beyond these efficiencies, I think there is many other things that can be done. And because the PV, the goal is to produce more electricities. And so efficiency, lifetime, and cost, those are the parameters one consider. But for solar evaporations, those are also important parameters. But important thing is that for the solar evaporations, you can use that for various approaches, for various applications. For example, if you want to get water, then you not only just want to evaporate that, you also want to collect that. So condensation is also important, right? And not just evaporations. But when you want to treat the water, wastewaters, right? You want all the water go and collect all the salt. Then perhaps evaporation rate is important. And if you want to do the sterilization, it's steam temperatures, right? If you want to produce power, is another thing. So I think the beauty of this field is that you have multiple applications to go, and as a result, you have a multiple figure of marries. I think that that part people need to consider. So it's no longer evaporation rate game, or it's no longer efficient game. I think that's something I think I firmly believe in. Yeah. I don't know what Professor Peng Wang said.
Right, so I really agree with Zhujia, what Zhujia just said. So there are in this field many other pressing issues that deserve a lot of effort from anyone. Energy efficiency for the steam generation is only one of them. So based on what Professor Zhu mentioned, I think should while working on the energy efficiency for solar steam generation, gradually turn our attention to other important issues as well. This way, only by doing this together, we can push this important technology or process towards its real application to make a real impact. Thank you.
Great. I think you guys already demonstrated fascinating, like efficiency already, right? And I think I also agree with both of you that if you really look for a real application, you have to solve other aspects together with this efficiency issue to get the real thing down to the earth. Now, let me see. There are other material-based questions. about this PEO membrane and also your cooling material at the last part of Zhujia's talk. Now, I think because the question is talking about the practicability of the PEO membrane. Since PEO is a water-soluble polymer, so I think that what the audience worry about is the stability in the air, because it might be softened due to some wet environment, or even like immersed in rain, for example. I think that's probably about this. And a question related to this question is about, suggestion how to do this radial cooling for non-solar heat sources. I think you did include those parts, for example, for human bodies, but probably you can elaborate a bit more.
Yeah, thank you. I think that I think for radial cooling, right? It's the beauty of the radial cooling is that you can send heat to the universe without consuming the active energies, and that's the beauty. And of course, in order to enable the widespread applications, actually you want to consider quite a few factors, and stability is one of them. And of course, there are many other things like the cost, or the if you do it for human beings, right? How do they feel? But I think that for the outdoor activities, there is actually quite a few scenarios people I think are plausible. So I think the contribution for this work is that it can provide a molecular level design to contribute to this field, right? So that's I think that's the thing. It doesn't necessarily to be PEO, but I think so far we don't see stability issues for PEOs much under environment, right? So you can do that through passivation, through protection as well. So, but I think that it's really the insight you can do that tuning the molecular bondings to tune the infrared emissions. That's the thing I think we want to provide the communities these directions to really do it through scalable approaches. And of course, there are many other molecules you can choose, many other materials you can do. And but I do think that for the active cooling, right, you're cooling a certain part, but also you're creating more heat because it's always a heat engine, right? So the overall cooling is the overall issue is still there. The radial cooling is really the way you can send the heat to the universe. I think that part we're really excited about that, and I think there'll be more things can be done. And I already see quite a bunch of startups try to commercialize these technologies. I think people in industry perhaps can provide a more practical perspective for that. Thank you.
Right. How about for the PEO, for the first question? Is it practicability or stability of this membrane?
Yeah, we don't see the stability as an issue at this moment. Actually, we test that for quite a bit long time. But also, at the end, it also depends on the requirements of applications, right? So, how stable is stable? I think that people need to consider that. For example, early stage, people are talking about certain solar cells. You use that as electronic devices, right? You charge that, and it degrades over certain years, and then you do it again together with electronic devices. I think the stability we don't see that as an issue right now, and of course it might become issues once you apply to different fields. But we don't see as a technology bottleneck at this moment.
Okay, I think time is almost up. I would like to raise the last question, and this question is posted by Bo just now to both of you. The question is, I quote, more and more papers reported high photothermal efficiency, but obviously not caused by environmental evaporation. it may be caused by the mistaken calculation, the light source, or uncalculated evaporation area. However, it will be a disaster for the research group strictly follows the standard test conditions because the standard of publication in this field is alleviated. Are there any good solution to this problem? So I think the question is quite general, right? Try to not to do the wrong experiment, following the wrong procedures, or calculating your results through certain, not taking any some important issues into consideration. So any comments from both of you? I think Zhujia, you mentioned very earlier you did publish a comment paper in Jewel talk about some of the calculation and testing standards, right, or kind of protocols.
Yes, I share the concern from the audience. I think that as more and more people are jumping in, and of course we want this to be a vibrant communities, right? Then we welcome really all the new members, and it is an important field, and at the nexus of energy and waters, as Professor Peng Wang said. So at the same time, we need to be really careful about how do we do the measurement correctly. And we understand if it's efficiency too low, then you probably want to report it, right? It cannot be published. But at the same time, really need to be really very careful and conservative about how do we do the measurement. And the protocols we published, I think, only as a starting point. Of course, because it is still evolving field, right? We have a more and more understanding about it. But I think that there is difference. If you check all the details and you have concerns, we can always exchange the ideas and opinions. But we don't want to do the measurement unintentionally to boost your efficiencies, right? I think that's nobody really want. And also, there is more and more paper I see that they're claiming efficiency over 100%. I really don't want that paper how do we achieve the efficiency over 100%, right? That means the output is above input, then it doesn't really make sense. That means there is all the other energy sources coming up, right? So evaporation rate can be high, but efficiency cannot be over 100%. So people really need to check all the details and also go back to the basic principles to see how do we do this correctly. But I think it also happens at all the early stages of any field, right? If you look at the histories of PV committees, right? Also a lot of things also happened at the early stage of PV development. I think that's something as people more and more people become aware, then we can start to build more consensus and we can build a more sustainable communities on that. But I think we can start work on that. Yeah. Professor Peng, Professor Wang, please go ahead.
All right, so I just want to follow up briefly on what Professor Zhu just said. I share your concern with some, bloated evaporation rate. However, I also want to stress what we just mentioned previously, that there are many other opportunities in the field besides the water evaporation rate. So do not get very frustrated when you see some miscalculation for the solar vapor evaporation rate. Just focus on what you are working on. Focus on producing beautiful science, and this way you will gradually push your research and yourself towards a much better place. Thank you.
Okay, I think the time we already overrun by about 15 minutes, and that's due to lots of discussions. So I apologize if I cannot raise your question that you posted online. Please allow me to apologize. And then if you have further questions, I think you can just email both speakers if you want, directly, and to raise the question or read their papers. I think the last question, especially about the standard or calculation, I think it all exists in every field, especially in energy, because energy is talk about numbers, right? So numbers are very sensitive, and I work on energy storage and battery capacitor, also have tons of this, so-called calculations or efficiency or density issues. And we all agree that this is an existing problem. We should have more like standards. People should develop some standards as time goes. But I think that's the great thing about academic research. We can come across with lots of arguments and discussions, even though we have disagreements. Right. So let me thank those speakers again at the end of this wonderful EcoMat symposium for solar thermal energy. And I also would like to announce one thing is that both Professor Zhu Jia and Peng Wang has kindly agreed to be guest editors for our special issue theme on this solar thermal energy conversion and utilization. So more information will be posted online. And also EcoMat is making a WeChat channel and LinkedIn and Twitter accounts. So we'll be online shortly after. So we'll post more informations apart from what we have posted on several platforms. We'll also post information on those platforms so that everybody can follow up EcoMat much better and get the papers. So again, thank you very much. I hope that you can go to the website and read our recent published papers and submit to EcoMat, one of the very best journal in energy and environmental materials. Thank you very much. Thank you, Zhu Jia. Thank you, Peng Wang, and thank you, Yang Bo. Thank you, Zhu Jing. Thank you very much. I'll see you everyone again in the next EcoMat meeting webinar.
Well, thank you again. Yeah.
Have a good day.
Yeah, thank you, Jing and Bo.